In this video, we're going to work out 3 examples where we use the properties of the dot product to solve some problems. So let's just do a quick review of the properties of the dot product. So we have that the dot product is a product of vectors, so an operation on vectors, but it provides you a scalar as output. It could be positive, negative, or zero. And in fact, we learned that that depends on the angle between the vectors. If the angle is acute, it's positive. If it's obtuse, it's negative. And if it is a right angle, so the vectors are orthogonal, then the dot product is zero. And then super important is that a dot product of a vector with itself is the same as the square of its lengths, or its length. What else did we learn? The order of dot product doesn't matter. That's a commutative property. We have a distributive property across addition. And then we have this associative property for scalar multiplication with the dot product. Could also use FOIL, but we're not really going to use that in these examples. So our first example is we'd like to find the acute angle between the two lines with equations x plus 2y equals 7 and 5x minus y equals 2. Now, we don't really need to graph these to answer this question, but I think it's best for us to go ahead and look at the graphs so we can illustrate what our strategy is. So here I've graphed both lines. I solved x plus 2y equals 7 for y, and I got y equals negative 1/2 x plus 7/2. All right, well, we want to use vectors. So I'd like to be able to find a vector that's parallel to each of the lines and then find the angle between the vectors. Well, the slope of a line, we can really think of that as a set of directions. How do we move from one point to the next? So for example, the slope of the yellow line is negative 1/2. So to go from this point to this point, I would take 1 step down, 2 steps to the right. Well, how would I write that as a vector? 1 step down, 2 steps to the right. Well, that would be a vector whose vertical component would be negative 1. That's the 1 step down. And the horizontal component would be positive 2. That's 2 steps to the right. And I could do the same thing with my green line. Its slope is 5, which I'll write as a fraction 5/1. And that just tells me that to go from, say, this point to this point, I need to take 5 steps up, 1 step to the right. How would I write that as a vector? Well, that would be a vector where the vertical component is 5, positive 5, 5 steps up, and the horizontal component is 1 step to the right. So let's look at those vectors then on our graph. All right, there's a problem here. Do you see it? The angle between these two vectors is obtuse, and the question asks us to find the acute angle. Now, there's a couple of ways we could solve this. We could just calculate the angle between these two vectors and then subtract it from 180. That would give me the angle adjacent to it, and that would be the acute angle. But what I'm going to do is I'm going to look at the slope of the green line in a slightly different way. the slope is positive 5. Well, you can get positive 5 by taking negative 5, dividing it by negative 1. So that would mean, oh, really, I'm going from this step, this point to this point by taking 5 steps down, 1 step to the left. And how would I write that as a vector? Well, instead of having vector with positive components, I'm going to have the opposite of it with negative components. I just really taking our original vector and pointing it in the opposite direction. And so now I can use our formula for the cosine of the angle between the vectors. The dot product is positive 3. The length of A is going to be 4 plus 1, radical of 4 plus 1. And the length of B is radical of 1 plus 25. So my exact answer for this question would be that theta is inverse cosine of 3 over radical 25 times radical 26, which I guess I could have multiplied that out. That would give me what? Radical 130. But I'll just use my calculator and get a decimal approximation. That's about 74.74 degrees. All right, here's an interesting example. We're going to take two vectors, A and B, and we're going to use them to define a third vector, C. And this vector C is going to be defined as, we'll take the vector B, multiply it times the length of A, and then we'll take the vector A, multiply it times the length of B, and add those two together. And we'd like to show that C bisects the angle between A and B. Well, we could start with a diagram here showing that, okay, I'm going to have C, it's going to be between A and B, and I'd call the angle between A and C alpha, the angle between C and B beta. But we can actually do better. We can actually give a geometric proof of this. And so let's think about that. This is worthwhile. Let's go back to our graphical addition of vectors. So I'm going to take the vector A that I have here, multiply it times the length of B. And suppose that gives me this vector here. So it's parallel to A, but it's a little bit longer. It is because it's been multiplied by the length of B. And then I'll take this vector B, and I'll multiply it times the length of A. And I'd like to add those two together. Well, my graphical addition would say, okay, I would take the tail of the blue vector and put it at the head of the red vector. But look at this. The length of the red vector would be the length of B, which is just a scalar, times A. And I can factor that scalar out in front, so that would just be the length of B times the length of A. And what about the length of this blue vector? Well, that would be the length of, the length of A, which is a scalar, times the vector B. And I can factor that scalar, the length of A, out in front. And I get the length of A times the length of B. Now that's very interesting. Well, let's complete our vector addition. Actually, I completed it in both ways. So here's my vector C. And I put this other red vector here because, well, what geometric shape do these vectors cover? They actually cover, well, not only a parallelogram, which is what I wrote, but since they have equal lengths, uh, it's not just a parallelogram. It is a rhombus. But it doesn't have to be a rhombus because the geometric property is that a diagonal of a parallelogram is going to bisect the angle made by its sides. So from geometry, we could give a geometric demonstration that C bisects the angle between A and B, because the angle between A and B remains the same even when I stretch out both of those vectors by multiplying A by the length of B and multiplying B by the length of A. But what we're trying to practice here is the properties of the dot product. So let's see if we can give an algebraic proof. So what we'd like to show is that alpha is the same as beta. If alpha is the same as beta, then we'll know that C bisects the angle between A and B. So let's calculate alpha. Well, let's start by calculating cosine of alpha. We're going to calculate cosine of alpha using our formula here. We'll do it one step at a time. So the first thing I'm going to do is in the numerator, so on top, I'm going to replace C with its definition. Then what I'm going to do is use the distributive property to take A dotted with the first term and A dotted with the second term. And when I do that, I'm going to use the property that I can factor out these scalars. The length of A is a scalar. The length of B is a scalar. I can factor those out in front of the dot product. So I would get the scalar length of A times A dot B, the scalar length of B times A dotted with A. So I took A dotted with B, multiply that times the length of A dotted with A, and multiply that times the length of B. All right, but what was that real important property that we learned? Oh yeah, the length of a vector, a vector dotted with itself is the same as the square of its length. So let's replace that with the length of A squared. Well, now I have a common factor in the numerator, which is the length of A. I can factor that out. And now the length of A is a factor of the numerator. It's also a factor of the denominator. So a scalar over itself is a form of 1. So that will divide to make 1, and I simplified to having just A dot B plus the length of A times the length of B all over the length of C. And that's cosine of alpha. Okay, so let's calculate cosine of beta. So I wrote over here that we found that the cosine of alpha is A dot B plus the length of A times the length of B all over the length of C. Let's do the calculation for the cosine of beta. So I use our formula. And again, my first step is going to be in the numerator, I'll replace C with its definition. Then I got to use the distributive property again. So I'll dot B with B, and the length of A will be in front. I'll dot B with A, the length of B will be in front of that dot product. All right, well, I actually wrote it on the right, but you know what I mean. So I'm going to use the same idea I did before. B dotted with itself is the same as the length of B squared. Well, now I have a common factor in the numerator of the length of B. So let's factor that out in front. And now I have a common factor in the numerator and the denominator. I have length of B over itself, a scalar, non-zero scalar, divided by itself makes 1. So this is going to simplify then to, well, A dot B, I just changed the order in which I wrote this, plus the length of A times the length of B all over the length of C. And sure enough, that is the same as cosine of alpha. So I've got cosine of beta equals cosine of alpha. There's one more thing that we have to note, and that is that the cosine function is 1-to-1 on the interval from 0 to pi. So since it's 1-to-1, if I have cosine of alpha equals cosine of beta, then I can conclude that alpha equals beta. And so if alpha equals beta, we can say that C bisects the angle between A and B. All right, in our last example, we have a box which is 12 centimeters long, 9 centimeters wide, and 8 centimeters high. And we're going to use vectors to find the angle between the diagonal of the box and the diagonal of its base. Well, we really need a picture here. So here is the box. And then let's draw in the diagonal. So the diagonal of the box really means you go from one corner to the opposite corner. So if you want to think of it this way, the lower left front to the upper rear and right corner. Now, I can see what the components are based on the lengths here. I am going 12 in the x direction, 9 in the y direction, and 8 in the z direction. Now let's draw the diagonal of the base. And I can write components for that vector too. It's going to go 12 in the x direction. It's going to go 9 in the y direction, and then 0 in the z direction. So now to calculate the angle, we can just use our formula for the cosine of that angle, form the dot product, and calculate the lengths. And you can see here that, well, first of all, this simplifies. Radical 225 is going to be 15. Radical 289 is 17. And 15 goes into 225 15 times. So we're left with cosine of theta is 15 over 17. So my exact answer would be theta is inverse cosine of 15 over 17. But taking out my calculator, that tells me it's about 28.1 degrees.